Limiting reactants. This is what I talked about yesterday, in that this is a really fun part to this chapter because it actually gives an application to the math that we've been doing. So if we were to look at an example of this, so like planning a meal, let's say that you go to the store and you buy a package of brats, comes in a package of 5, a package of cheese slices, which have 16, and a package of hot dog buns, which have 8. If we wanted to predict the amount of meals that you could use with these ingredients, if we went by only the brats, you'd be able to make 5 meals. If we went by only the cheese slices, based just on the cheese, and you had unlimited everything else, you could only make 16 meals. And if we went by the hot dog buns and only the hot dog buns, and let's say you had unlimited everything else, but 8 hot dog buns, you can only make 8 meals. Well, of course, you don't have unlimited ingredients. So the question then is, based on these amounts, how many meals are you actually going to make? And of course, the answer is 5. Because you will never get to 8 or 16 because you are going to run out of brats as soon as you get to 5. And once you run out of brats, you're done. You can't make any more meals. No one wants just a hot dog bun stuffed with cheese, although right now that does sound very good. And this is what the limiting reactant is that in every chemical equation, every chemical reaction, your reactants, those things that you start with, are like the brat and the cheese and the bun, is that they are ingredients to a combination. And you are going to run out of one of those things before you run out of everything else. Because it is, for all intents and purposes, it is impossible to have the perfect ratio, the perfect amount of all reactants in order for them to combine so that you have nothing left over, because atoms are really small, right? And in a speck of dust, there are billions upon billions of atoms. It's just not possible to have the right amount. So you are going to run out of a singular, a reactant, and that's going to cause the reaction to stop. So in the previous examples, the brats were our limiting reactant. Once they were gone, the meal making was over, the reaction was over, and we were not making any more product. So let's look at how this actually works with what we're doing. Now, ultimately, what we're doing is nothing new. All of the calculation stuff that we just took a quiz over, we are doing the exact same calculations. There is 0 things new. The only thing that we are adding is an interpretation of those calculations. So if we look at this example, how many moles of water is produced when 2.3 moles of oxygen and 2.3 moles of hydrogen react? So there are our starting amounts. So what we are trying to figure out is, what are we going to run out of first? And the way that we want to go about this is we want to take our amounts given, write them down, and then we want to convert them to a product. Now, in this case, we only have one product, which is the water. So we're going to go through the process of converting 2.3 moles of oxygen into moles of water. And so we need the mole ratio, which is 2:1. So the moles of oxygen go on bottom so that they cancel. And what we find is that with 2.3 moles of oxygen, we can produce 4.6 moles of water. Now, we want to do the exact same calculation, but this time with the hydrogen. So it's a different mole ratio. It's a 2:2 ratio, as you can see from the coefficients in the equation. Hydrogen goes on bottom, and so with 2.3 moles of hydrogen times 2 divided by 2, we can make the exact same amount of water. So as we start combining the oxygen and hydrogen together, our bucket of water is going to start filling up. And once we get to 2.3 moles of water, we are going to run out of hydrogen. We're never going to get to 4.6. And so we have to go with the smaller amount. And so based on this calculation, this is how we know that the hydrogen is the limiting reactant. And that's our process. We just take the reactants, the amounts that were given in the problem, and then we just convert them to moles of whatever product we're asking for. And then whatever you have the least amount of, that's your limiting reactant. So let's do one more example. This time you are starting with grams of the two reactants, so grams of sodium hydroxide and grams of barium chloride. And we want to know how much sodium chloride, NaCl, is produced in terms of grams. So we're going to need the mole ratio for all of these things. So here's the mole ratio for our reactants, so sodium hydroxide to salt and barium chloride. But because we have grams, we are also going to need the molar masses. And so here are your molar masses for these compounds. And so what we're going to do is we're going to just do one big long gram to gram conversion. So we're going to convert our grams of sodium hydroxide into grams of sodium chloride. So we're just going to go through our process. Now, I would encourage you at this point in time to maybe pause the video and try to do this example on your own. But first, we're going to use the molar mass. Divide by the molar mass of sodium hydroxide. That gives us moles. And then we're going to use the mole ratio, which is 2 to 2, as you can see from the balanced equation. And then we're going to use the molar mass of sodium chloride to help us get to grams of sodium chloride. And so we see that with 7.5 grams of sodium hydroxide, we can make 11 grams of sodium chloride. And so now we're going to do the exact same thing, but this time with the barium chloride. So the 10.5 grams barium chloride, which is in the problem, divide by the molar mass to convert it to moles. Use the mole ratio to convert to moles of salt. And then multiply by the molar mass of sodium chloride. And we find that we get, when we do the math, that we can make 5.9 grams of sodium chloride. So as we start combining the NaOH and the BaCl2, we're going to start making salt. But once we get to 5.9 grams, we are going to run out of barium chloride. So we look at the least amount, which in this case is 5.9, and so I know that barium chloride is my limiting reactant.